Hi and welcome to our PEL CAPRE workshop. In this short tutorial, I will demonstrate how to calculate the flow rate of material to a fail-open control valve. In this specific scenario, a client wanted me to determine whether a bursting disc was adequately sized on a pressure vessel. One of the relief scenarios in this case was the potential to overpressure the vessel through a fail-open control valve upstream of a heat exchanger, which would result in high-pressure steam entering the system. The assessment was to verify whether the bursting disc could adequately relieve the steam entering the vessel. Quickly show a sketch to illustrate this problem in hand. So we have steam entering the steam header, going to the control valve, to a heat exchanger and into the vessel, which is protected by a bursting disc set at 0.35 bar gauge. To determine how much steam can flow through this control valve, i.e. the required relief rate in this example, we can utilize a Capre sheet, specifically the high pressure source control valve sheet. So if I open up a blank Excel sheet, and open up the high pressure source control valve vapor Capre sheet. So I've used this Capre sheet numerous times to determine flow rates of fluid through control valves. I've also used this sheet when sizing control valves and determining KVs and CVs of these valves by specifying flow rate and other conditions that are known. So the first thing we can do is name the fluid steam in this example. Now we need the physical properties of the steam at upstream conditions. We need to find these properties at the highest pressure that the steam can be prior to it entering the control valve, as this will give us the maximum flow rate through the valve and hence give us the worst case scenario. If I flip back to the sketch, you can see that the steam header has its own relief valve, which is set at 6.5 bar gauge. Therefore, we can assume that the highest pressure the steam will be before lifting this relief valve is 6.5 bar gauge. To determine the physical properties of steam at these conditions, I can utilize the PHYSPROPS Capre sheet. So if I click on Calculate Properties, add a component, which is steam in our example. Now we need to specify the conditions of the steam. So we know the steam is at 6.5 bar gauge. And Capre has a function which, if we specify the unit, should be the unit conversion for us. So we're going from 6.5 bar gauge to bar absolute, and does conversion for us. Now the calculation type in this example, I'll specify bubble point from pressure. So you'll notice that I obtained the properties of 6.5 bar gauge steam at its saturated conditions, which I will explain in a bit more detail further on. So if you click OK on that, all of the properties of steam at 6.5 bar gauge at its saturated conditions are tabulated in the PHYSPROPS Capre sheet. An advantage of utilizing the Capre sheet, Capre PHYSPROPS sheet, is that we can link the properties from the control valve Capre sheet to this PHYSPROPS sheet. Therefore, if there's any changes to the properties of the material that the user wants to make, it will automatically change on the control valve sheet. So if the conditions of steam had changed, you can change the conditions in the PHYSPROPS sheet and it will automatically update on the control valve Capre sheet as you've linked them. So if I just link the density, the kinematic viscosity, as well as the ratio of specific heats. One thing to be wary of, however, are the units of the properties. The units in the control valve sheet may be different to the ones given in the PHYSPROPS sheet. So to ensure that the units are consistent across both the sheets, what you can do is link the units in the control valve sheet to the units in the PHYSPROPS sheet. I don't need to do this in my specific example, as the units are identical on both sheets. The next input required is the steam temperature. This goes back to why I calculated the properties at saturated conditions. Since in this example we didn't know the temperature of steam at 6.5 bar gauge, we can assume saturated conditions as a conservative estimate. The temperature makes a difference to the volume flow calculated at the bottom. So if I link the temperature, again ensuring that the units match as well. So we've already specified the high pressure or the upstream pressure of the steam, which was 6.5 bar gauge. We also need to specify the low pressure or P2 in this example. So in my case, I wanted to calculate how much steam can flow through this control valve and hence check if the bursting disc can fully relieve this material. So if I flip back to the sketch, you can see that the vessel is protected by the bursting disc set at 0.35 bar gauge. So in my example, P2 or the low pressure will be 0.35 bar gauge. The next property we need is the flow coefficient of the control valve. This can be either its kV or CV depending on what is provided. In my example, the client provided the kV of the valve, which was 360 meters cubed an hour. The nominal valve size of this control valve was 200 millimeters. The next three parameters are the pressure differential ratio factor, the valve style modifier, and the liquid pressure recovery factor. There are notes on the sheet explaining what these inputs define. Additionally, you can pull up the table in IEC 60534, which is available on the CAPRE tab, to obtain accurate numbers for these parameters. In my example, since the client did not provide these values, I inputted a 1 for the pressure differential ratio factor as a conservative estimate, as well as a 1 on the valve style modifier and 1 on the liquid pressure recovery factor, as these were not known and do not affect the capacity of the valve. Finally, I needed the upstream and downstream piping diameter. In my example, these were the same as the valve size at 200 millimeters. So with all these required inputs, you can see that 40 tons an hour of steam will pass through the control valve at the specified conditions. This gave me the relief rate in my assessment, and I was able to determine if this relief scenario could be disregarded or whether further work would be required on the upstream relief device. Full details on what this sheet is doing is available on CAPRE's online help. Thank you for listening to this short tutorial, and I hope it proved useful.